Is it audible clearly? Yes? Okay, fine. So let us start. I hope it is audible to everybody. So, partial differential equations. In that actually, we discussed the family of surfaces, right? So, we will see some other examples based on that, and then we can go to the solution of the linear differential equations. Now, note down one problem. Eliminate A and B from eliminate A and B from AZ plus B equal to A square X plus Y. So can you solve this? So this is actually forming the differential equation. This is straightforward and simple. Anybody got the answer for this? This is straightforward forming the differential equation, right? So there is no difference between the ordinary differential equation and the partial differential equation while forming the differential equation by eliminating the arbitrary constants, right? Now here, this is, if you take the derivative A dou z by dou x is equal to plus 0 is equal to A square, or dou z by dou x equal to A. So this is equation number 1. And the second one is, take the derivative with respect to y, then A into dou z by dou y plus 0 is equal to 0 plus 1, right? Or dou z by dou y is equal to 1 by A. So from equation number 1 and 2, so you replace the value of A, that is, so A into dou z by dou y equal to 1. It implies A is dou z by dou x and then into dou z by dou y equal to 1, or PQ is equal to 1. This is the differential equation. Got it? Understood? Here actually, why I have given this example is, here if you notice, there are two different arbitrary constants here. Now, if there are only two arbitrary constants and then other than z, or z can be expressed as a function of x comma y. So two independent variables are there. So if there are two independent variables and two arbitrary constants, then usually the order of PDE is usually 1. That means if you notice, this is dou z by dou x and dou z by dou y. These are the only two terms that are present in this differential equation. Got it? So the order of the differential equation is 1 itself. So when there are two independent variables and two arbitrary constants, usually usually the number of variables or the number of independent variables is exactly equal to the number of arbitrary constants. Then the order of the differential equation is 1. So this is one principle. Got it? Note down this. Noted? Note down one more. Form the differential equation or eliminate a comma b comma c from z is equal to ax plus by plus cxy. Now here z is a function of x comma y, but so z is a function of x comma y. So two independent variables. Two independent variables, but the number of arbitrary constants are more than 2. So then the order of the DE will be usually more than 1. So this is the principle. Now from this actually can you try to avoid these arbitrary constants and then form the differential equation? Now if you notice in this particular equation, so z is equal to ax plus by plus cxy. Now if you take dou z by dou x, this value is going to be, so a plus cy. Similarly, dou z by dou y is equal to b plus cx. If I take the second derivative, then dou square z by dou x square is equal to 0. Dou square z by dou y square is equal to 0. Dou square z by dou x dou y. So this value, so either from this equation or this equation, both are actually, it will be c. And then from this, so here actually z is equal to ax plus by plus cxy. Now if I take from this equation, so this is equation number 1, this is equation number 2, and this is equation number 3, this is 4, and this is 5. So from this equation, I wanted to get this value of ax plus by, so that actually I can simplify this, that is x dou z by dou x is equal to ax plus cxy. Similarly, y dou z by dou y is equal to by plus cxy. Now if I add these two together, x dou z by dou x plus y dou z by dou y, right? So y dou z by dou y is equal to ax plus by plus 2cxy. Got it? So here actually from this equation I can write ax plus by is equal to z minus cxy. So if I replace it here, z minus cxy plus 2cxy. So this is z plus cxy. Got it? But the c value is dou square z by dou x dou y. Then x dou z by dou x plus y dou z by dou y is equal to z plus dou square z by dou x dou y into xy. This is the differential equation where we have eliminated the arbitrary constants, but the order of the differential equation is more than 1. Got it? Understood? Okay. Note it down. Note down one more. So this is actually eliminating the arbitrary constants to form the partial differential equation. Now, in case of partial differential equation, so there is a possibility of eliminating the arbitrary functions as well. So that won't be there as part of ODE, but this is specific to PDE. So note down one such kind of case. Eliminate the arbitrary function. Eliminate the arbitrary functions. F, small f and capital F from y equal to f of x minus at plus capital F of x plus at. So this is actually the solution of a wave equation. Now let us see. So there are two different arbitrary functions are there here, small f and capital F. So here if you take the derivative, so dou y by dou x is equal to f dash of x minus at and then plus f dash of x plus at. So this is by taking the first derivative, right? And then if I take the derivative with respect to t, dou y by dou t is equal to f dash of x minus at into minus a plus f dash of x plus at into plus a. Got it? And then if you take the derivative of this again, dou square y by dou x square is equal to f double dash of x minus at plus f double dash of x plus at. Now if you take the derivative again for this, dou square y by dou t square is equal to, so this is f dash of x, f double dash of x minus at into minus a whole square plus f dash of x plus at into a square. So if you take a square from this, then what you are left over is f double dash of x minus at plus f double dash of x plus at. But this is equation number 1. So f double dash of x minus at plus f double dash of x plus at is equal to dou square y by dou x square. Now this you can replace as a square dou square y by dou x square. So in short, dou square y by dou x square dou t square is equal to a square times of dou square y by dou x square. Got it? Understood? So this is elimination of arbitrary functions. So no more f involved there. Note down one more. So form a partial differential equation by eliminating the arbitrary function phi from phi of x square plus y square plus z square, comma z square minus 2xy equal to 0. Now form the differential equation by eliminating the arbitrary function. So that's what I told you, right? So if the number of variables, in case of ordinary differential equations, the number of arbitrary constants is exactly equal to, so number of arbitrary constants, right, is exactly equal to the order of the differential equation in case of ODE. But in case of PDE, that is a little bit different. So there are two independent variables in case. Suppose z is a function of x comma y. So I explained in the previous problem. So if z is equal to x comma y, and then the function z is having exactly two arbitrary constants, you have to differentiate only once, but with respect to x once and with respect to y once. Got it? So then actually you can eliminate the arbitrary constants because you have got two different equations with the differentiation with respect to x once and with respect to y once. So in that case, the order of the differential equation is only 1. Suppose if the number of arbitrary constants are more than the number of independent variables x comma y, then the order of the differential equation is exactly equal to the number of extra arbitrary constants. Got it? Suppose if there are 3 arbitrary constants and 2 independent variables are there, then the order of the differential equation is 2. Got it? Suppose if it is an arbitrary function elimination, then actually the number of arbitrary functions is exactly equal to the order of the differential equation. Got it? Understood or not, Deepak? Okay. So here actually there is only one function phi. So now actually this phi is a function of u comma v equal to 0, where u is equal to x square plus y square plus z square and v is equal to z square minus 2xy. Right? So this is the function. Now phi is a function of u comma v. Now if you take the derivative with respect to x, so taking the derivative with respect to x, then so it is going to be dou phi by dou u into, so dou u by dou x plus dou z by dou x into dou u by dou z. Got it? So this is dou phi by dou v into dou v by dou x plus dou z by dou x into dou v by dou z. This is equal to 0. So this is taking the derivative with respect to x once. Got it? So this you can further simplify as dou phi by dou u into dou u by dou x plus dou z by dou x is p and dou u by dou z plus dou phi by dou v into dou v by dou x plus p times of dou v by dou z is equal to 0. So this is equation number 1. In that you can replace this dou u by dou x from this. So from this equation, dou u by dou x is equal to 2x and dou v by dou x is equal to minus 2y, and so dou u by dou z is equal to 2z, and dou v by dou z is equal to 2z. So if you replace it here, dou phi by dou u into dou u by dou x is 2x plus dou u by dou z is 2z, 2z into p plus dou phi by dou v into dou v by dou x. So dou v by dou x is minus 2y plus p times of dou v by dou z is 2z is equal to 0. So if you cancel 2 on all, then x plus zp times dou phi by dou u plus minus y plus pz into dou phi by dou v equal to 0. This is equation number 1. Got it? I hope you understood how I have done the derivative. Understood? This part, see this, we have the function he has given phi as this one. Now, the phi actually I have taken as function of u comma v, where u is x square plus y square plus z square and v is z square minus 2xy. And then I have done the derivative of this particular function with respect to x. Then if I take the derivative of this particular function with respect to x, then this is dou phi by dou u I can do because I have the function of u comma v, not x comma y. But u is again internal function of x comma y comma z, and v is again internal function of x comma y comma z. So if you want to take the derivative by chain rule, dou phi by dou u, you have to do the derivative with respect to u first and then with respect to v next. But when you are doing the derivative with respect to u, then u is internally a function of x comma y comma z. So here actually you need to take the derivative of u with respect to x again. But here x is, so u is a function of x comma y comma z. But you need to take the total derivative. So for that actually what you need to do is dou u by dou x into dx by dx plus dou u by dou z into dou z by dou x. But you cannot take dou u by dou y because that is an independent variable. So z is dependent variable because z actually is expressed as a function of x comma y. So then dou phi by dou v also you will be doing exactly in the similar manner. So with respect to x only, this part. So you are doing with respect to u and then with respect to v, and in that dou v by dou x into dx by dx, dou v by dou z into dz by dx. Got it? So this is actually finding out the derivative, partial derivative when there are multiple variables are present. So this actually you have to learn as part of partial differentiation. Here, this is the method we adopt in case if you want to find out. See, we are doing the partial derivative here, right? So when we are doing the partial derivative, so z is usually expressed as a function of x comma y. So in such case, dou z by dou x you want to find out, not dz by dx. So what you have to do is here dou f by dou x actually you will be finding out straight away because x comma y are treated as the independent variable and z is the dependent variable on x comma y. This is the standard convention. Got it? So that's the reason actually when u is a function of x comma y comma z, so dou u by dou x into dou x by dou x, dou u by dou z into dou z by dou x. But you should ignore y. Here also, when you are doing the derivative with respect to x, as x is an independent variable and y is an independent variable, but z is a dependent variable on x comma y. So here dou z by dou x comes and dou v by dou z comes. Now exactly in the similar manner, so this is with respect to x, right? Now actually taking the derivative with respect to y. Then you have to take the derivative with respect to y. That is dou phi by dou v, dou phi by dou u into dou u by dou y plus dou z by dou y into dou u by dou z plus dou phi by dou v into dou v by dou y plus dou z by dou y into dou v by dou z is equal to 0. Now again we have to do the simplification exactly in the similar manner. Got it? You note down this first and then actually I am going to erase it and then simplify. Done? Noted? Noted down? Okay. Now here, now from this equation if I write it here, x plus pz into dou phi by dou u, so equal to y minus pz dou phi by dou v. So this is equation number 1. Now if we again simplify this, the second equation, dou phi by dou u into dou u by dou y. So I have to calculate dou u by dou y. So dou u by dou y is equal to 2y and then dou v by dou y minus 2x dou v by dou z so this is 2z, dou u by dou z, this is also 2z. So if I put it here, so dou u by dou y I can write as 2y plus dou z by dou y into, so dou z by dou y is q and dou u by dou z, so dou u by dou z is 2z plus dou phi by dou v into dou v by dou y is minus 2x plus dou z by dou y is q and dou v by dou z is 2z equal to 0. So if you cancel 2 from this, then y plus qz into dou phi by dou u is equal to x plus x minus qz times dou phi by dou v. So this is what finally we have got. Now this equation, so from this equation you can calculate from this dou phi by dou u divided by dou phi by dou v is equal to y minus pz divided by x plus pz. From this equation, dou phi by dou u divided by dou phi by dou v is equal to x minus qz divided by y plus qz. So this is equation number 3 and this is equation number 4. But equation number 3 is equal to equation number 4. Now you can get y minus pz divided by x plus pz is equal to x minus qz divided by y plus qz. So this is the required PDE. Got it? Understood? I just equated these two. Any questions on this? This is how actually, so this is a standard procedure when we have the arbitrary function which is having inherent two different functions together. So this is the methodology what you need to adapt. Okay. Now, okay. So in case of quasi-linear equations, so a quasi-linear equation is nothing but a partial differential equation of a specific format. So this is also called as Lagrange's form of quasi-linear partial differential equation. So what this quasi-linear says is, suppose if the differential equation is a function of x comma y comma z multiplied by dou z by dou x plus q is a function of x comma y comma z multiplied by dou z by dou y, and this is equal to r, which is again a function of x comma y comma z, then this differential equation is called as quasi-linear differential equation. Now, if this is only a function of x comma y independent of z, then it is simple linear. So this is called as the simple linear equation, and r is a function of x comma y comma z, but z power 1. So z is of first degree. Then this is called as semi-linear equation. But a little complex than this is r of x comma y comma z, but z can be any power, any degree is called quasi-linear. Got it? So this is a quasi-linear equation. So left side is same. It may be a function of x comma y comma z getting multiplied by dou z by dou x, and q is a function of x comma y comma z getting multiplied by dou z by dou y. Is a function of r of x comma y comma z, where if it is independent of z, z power 0, then this is called simple linear. If it is z power 1, then it is semi-linear equation. If z is of any power, then it is a quasi-linear. It is simply a function of x comma y comma z. Got it? So this is quasi-linear equation. We have in our syllabus the quasi-linear equation. In short, we write this as capital P into small p plus capital Q into small q is equal to capital R. So this is a quasi-linear equation. Got it? So if it is a quasi-linear equation, the straightforward solution is exactly equal to dx by p, capital P, is equal to dy by capital Q is equal to dz by capital R. So this is the solution of a quasi-linear equation. Got it? Note down this. So if this is the format, then this is the solution for it. Proof is not important. That is a little bit complex to understand, but is of no use. So that's why actually all the problems, whatever is asked till now in UPSC is only straightforward based on this principle. Yeah, this is a solution for all the three cases. Yeah. Got it? Okay. Based on this, note down one problem. So start with the simple one. Solve y square z by x. Y square z by x times p, small p, plus xz cube is equal to y square. So solve this. This is a simple linear case. So the straightforward solution for this is dx by y square z by x is equal to dy by xz is equal to dz by y square. Now you can take any two. So first actually we'll take these two. So this is dx by y square z by x is equal to dy by xz. Now this x you can cancel out, and then this is x dx by y square is equal to dy by x, or x square dx is equal to y square dy. Now if you take integration on either side, then x cube by 3 equal to y cube by 3 plus c, or x cube minus y cube is equal to some random constant k. So this is equation number 1. Got it? Now if you take these two, then dx by y square z by x is equal to dz by y square. This y square will cancel. Then x dx is equal to z dz. If you take integration on either sides, x square by 2 is equal to y square by 2 plus some random constant, let us say k1. Now x square minus y square is equal to k1. Now this is equation number 2. At the end you need to write the solution as phi of k1 comma k2 equal to 0, or phi of x square minus y square comma x cube minus y cube equal to 0. So this is the solution, or in other words it can be written as x square minus y square is equal to some random function of x cube minus y cube. So any form actually is possible to write. You just need to mention this. So this is the solution where this is an arbitrary function. Yeah. So this is what you say here, it is correct. Yeah. This is z square. Got it? So this is how actually a quasi-linear equation usually solved. Based on this, note down one more. Solve the differential equation. x square plus 2y square p minus xy cube is equal to xz. So this is the semi-linear equation where z is present on the right side. Now actually can you solve this equation? So write the auxiliary equation